Hello students, we started with group 15 elements and we have seen their occurrence, physical properties and chemical properties. In today's video we are going to see some of the different behavior of nitrogen from the rest of the family. And let's recall what are the elements present in group 15. We have nitrogen, phosphorus, arsenic, antimony and bismuth. Usually, the first member of these groups behave differently from the rest of the members. So, first member of group 15 is nitrogen, and nitrogen behaves differently from the rest of its members because of its small atomic size, high electronegativity, high ionization enthalpy, and absent of d orbital in its valence shell. So, compared to all the other members of the family, nitrogen has the smallest size. And as you move down the group, electronegativity decreases. So that shows nitrogen is highly electronegative compared to the rest of the family members. Same way, as you move down the group, ionization enthalpy decreases. So again, nitrogen has got the highest ionization enthalpy in group 15. Same way, when you look at the electronic configuration of nitrogen, you have 1s2, 2s2, 2p3. What is absent? D orbital is absent in its valence shell. These are the main reasons why nitrogen differs from the rest of the members. So now we know the reason why nitrogen is behaving differently. Now let's see some of the anomalous behavior. Anomalous means behaving differently from the rest. So now we will see some of the anomalous behavior of nitrogen which are supported by some of its characteristics or properties. First one, p-pi multiple bond. Nitrogen can form p-pi multiple bonds with itself and with other elements like carbon and oxygen. When we say p-pi multiple bond, we actually mean overlapping of the p orbital of one atom with the p orbital of another atom. You would have studied about this in grade 11, chemical bonding and molecular structure. So nitrogen is capable of forming p-pi multiple bonds with itself. So that's why we have N triple bond N. Nitrogen bonds with itself via pi bonds and also sigma bonds. And not only with itself, nitrogen can form p-pi multiple bonds with other elements like carbon and oxygen. And why particularly carbon and oxygen? Because with elements of high electronegativity and small size, these two have high electronegativity and small size, and that's the reason nitrogen is capable of forming p-pi multiple bonding. The other elements present in the group 15, what are the other elements? Phosphorus, arsenic, antimony and bismuth. They are not capable of forming any p-pi bonding because their atomic orbitals are so large that they cannot have effective sideways overlapping. So when you say p-pi overlapping multiple bonds, so this is a p orbital and this is another p orbital, they overlap. This is sideways overlapping. This is not possible in the other elements of group 15 because of their size of the atomic orbitals. It is very big, so this overlapping is not effective. So since nitrogen is capable of forming this p-pi multiple bonds, nitrogen exists as a diatomic molecule with a triple bond. So there is a triple bond between two nitrogen atoms. Of that triple bond, one is sigma bond, the other two are pi bonds. Whereas the other elements in group 15, as they do not form p-pi multiple bonds, they form single bonds. See, phosphorus is bonded by a single bond with another phosphorus. Arsenic is bonded by a single bond, and Sb is also bonded by single bond. Bismuth, it forms metallic bonds because it is metallic in nature. And nitrogen exists as a diatomic molecule, which means N2. Whereas other elements of the group, they exist as tetraatomic molecules, P4, AS4, SB4. I just told you N2 molecule, two nitrogen atoms are bonded by a triple bond, and the N2 molecules are held together by weak van der Waals forces of attraction. One N2 molecule is bonded or attracted to another N2 molecule by weak van der Waals forces of attraction, and they can be easily broken. And that's the reason why nitrogen is a gas at room temperature. But the rest of the members, because of their bigger size and due to the force of attraction holding the tetraatomic molecules, as I told you, P4, AS4, because of that, and these force of attraction are quite strong and they cannot be broken at room temperature. Therefore, these are all solids at room temperature, whereas N2 is a gas and P4, AS4, SB4 are all solids at room temperature. So we are seeing the anomalous properties of nitrogen. The first one, it is capable of forming p-pi multiple bond because of its small size and high electronegativity. So nitrogen forms this multiple bonds with itself and also with other elements like carbon and oxygen. And the next property is catenation. You know what is catenation? It is the self-linking of atoms. We know about carbon's catenation property. The reason why we have a separate branch of chemistry for organic compounds is because of this catenation property of carbon, because carbon can bond with itself and form a very long chain. That self-linking of atoms is called as catenation. And the element of group 15, they also show the property of catenation, but to a small extent, not like carbon. Among all the members, phosphorus has the maximum tendency for catenation, and nitrogen has the little tendency for catenation. The reason is, since N bond N single bond is actually weak due to interelectronic repulsions, because there are lone pair of electrons present on the nitrogen atoms of N single bond N, and it is having a small bond length. So there will be electron-electron repulsions. So when there is repulsion, you cannot form a strong bond. So catenation tendency of nitrogen is very little. So to conclude, nitrogen has little tendency for catenation. And the next one is d-pi, p-pi multiple bonds. We just saw that nitrogen is capable of forming p-pi, p-pi multiple bonds, whereas the rest of the family members, they are not capable of doing so because of their big size of atomic orbitals, and overlapping cannot be effective. And nitrogen can form p-pi, p-pi multiple bonds because of its small size and high electronegativity, and overlapping will be to appreciable extent. And now we are talking about d-pi, p-pi multiple bonds. So here a d orbital is overlapping with the p orbital, and obviously nitrogen cannot form d-pi, p-pi multiple bonds because of absence of d orbitals in its valence shell. We know when you look at the electronic configuration, we don't have d orbitals in the valence shell of nitrogen, so nitrogen cannot form this multiple bonds. But the rest of the members in the family, they have d orbitals in their valence shell, so they are capable of forming d-pi, p-pi multiple bonds. So that is the reason why phosphorus can form compounds of type R3p double bond O, R3p double bond CH2. Phosphorus can form this multiple bond because it can form d-pi, p-pi multiple bonds. But this compounds are not possible with nitrogen. This R stands for alkyl groups. So nitrogen cannot form R3N double bond O, R3N double bond CH2, compounds like this. But phosphorus can form because it can form d-pi, p-pi bonds as it contains vacant d orbitals in its valence shell. Not only phosphorus, both phosphorus and arsenic can form d-pi, p-pi bonds with transition elements. You know what are transition elements? We have seen in coordination compounds, d block elements can, the metals can coordinate with the ligands to form coordination compounds. So when phosphorus and arsenic form compounds like this, PC2H5 thrice, C6H5 thrice, when these compounds act as ligands, then phosphorus and arsenic can form d-pi bonds with transition elements. This is called as triethyl phosphine, and this is triphenyl or cyne. So these two, when they act as ligands, then phosphorus and arsenic can form d-pi bonds with transition elements. But all you have to understand here is nitrogen is not capable of forming d-pi multiple bonds. So they might ask you why phosphorus is capable of forming these compounds but nitrogen is not forming this, because of the absence of vacant d orbitals in its valence shell. Nitrogen cannot form d-pi multiple bonds, and that is the reason nitrogen is not forming these compounds. And the next anomalous behavior of nitrogen is that nitrogen is the most non-metallic, which means it is a typical non-metal, while the other elements are either semi-metals or metals. When you look at the oxides of nitrogen, nitrogen is capable of forming 5 oxides. We are actually seeing the anomalous behavior of nitrogen, how it differs from the rest of the family. So nitrogen is capable of forming 5 oxides with oxygen. When you take the hydride of nitrogen, how do you get the hydride of nitrogen? When nitrogen reacts with hydrogen, you will get NH3, which is ammonia, which is nothing but hydride of nitrogen. When you look at the hydrides of group 15 elements, only hydride of nitrogen is stable, whereas the other other hydrides are unstable. So NH3 is only stable. And when it comes to trihalides, except NF3, trihalides of nitrogen like NCl3, NBr3, Ni3 are unstable. We have seen this in the previous video when we discussed about the reactivity, chemical reactivity trends of group 15 elements. We have seen how these group 15 elements form oxides, hydrides and halides, and we have seen all these reasons why trihalide of nitrogen NF3 is stable, whereas rest of the halides, trihalides, are unstable. So these are the anomalous behavior of a nitrogen. So we started with group 15 elements. We have seen their general trends and we have seen why nitrogen is behaving differently. And the next part that we are going to start with is compounds of group 15 elements, especially nitrogen. So when we are going to learn about each group, we will be learning about compound of one particular element. Same way in group 15, we are going to study about the compounds of nitrogen. When we say compounds of nitrogen, we are going to actually see how to prepare those compounds and what are their properties and what are their uses. So under that topic, compounds of nitrogen, we are going to see about ammonia, nitric acid, and we are going to see dinitrogen also, which is nothing but molecular nitrogen, N2. So in the upcoming slides, we are going to see dinitrogen's preparation, properties and uses. Same way for ammonia and nitric acid, we are going to see their preparation, physical properties, chemical properties and their uses. So you will be learning a lot of equations. So be prepared and be clear in what you're learning. In today's video, let's just see about dinitrogen. Dinitrogen is also called molecular nitrogen or simply nitrogen. It is a colorless, odorless and tasteless gas, and we know it comprises nearly 78% by volume of Earth's atmosphere. Nitrogen was actually discovered by Daniel Rutherford in the year 1772, and you know it exists as a diatomic gas in the elemental state. Now we will see the preparation of nitrogen. There are two types of preparation: commercial preparation and laboratory preparation. When we say commercial preparation, we are talking about large scale preparation. So for commercial preparation, we are going to prepare dinitrogen from air, because you know 78% by volume is nitrogen. So you're going to take air and prepare nitrogen from that. Dinitrogen is prepared commercially from air by liquefaction and fractional distillation. We know how to do this liquefaction and fractional distillation. Fractional distillation is done by taking into consideration the difference in the boiling points of different liquids. So liquefaction is liquefying a gas, changing a gas into liquid. So you're going to liquefy and then do fractional distillation to get nitrogen. When liquid air is allowed to distill, dyed nitrogen having lower boiling point, which is 77.2 Kelvin, distills over first, leaving behind liquid oxygen whose boiling point is 90 Kelvin. So the one with the lower boiling point will distill out first, leaving behind the liquid with higher boiling point. So that's how we prepare dinitrogen commercially. Now coming to lab preparation. In laboratory preparation, we are going to follow three different methods to prepare nitrogen. First one is by thermal decomposition of ammonium dichromate and also thermal decomposition of sodium or barium azide. In the first preparation, we are going to prepare nitrogen from aqueous solution of ammonium chloride and sodium nitrite. What is the formula for ammonium chloride? NH4Cl. Sodium nitrite is NaNO2. See, nitrate is NaNO3, nitrite I is NaNO2. So NH4Cl plus NaNO2, you will get nitrogen plus water plus sodium chloride, NaCl, N2 plus H2O. So this is the first way of preparing nitrogen in the lab from aqueous solution of ammonium chloride and sodium nitrite. In this preparation, you will get small amounts of NO and HNO3 as impurities. This NO and HNO3 impurities can be removed by passing the gas, which means the nitrogen gas, through aqueous sulfuric acid containing potassium dichromate. So when you get nitrogen by this method, that nitrogen will have NO and HNO3 as impurities. So how can you remove that? When you pass this nitrogen gas containing these impurities through aqueous sulfuric acid, which contains potassium dichromate. So in that way you can remove NO and HNO3. And the second preparation of nitrogen is by thermal decomposition of ammonium dichromate. K2Cr2O7 is potassium dichromate. So if you want ammonium dichromate, instead of K, you're going to put NH4. So NH4 twice Cr2O7 is ammonium dichromate. So when you heat ammonium dichromate, you're getting N2 plus 4H2O plus Cr2O3, which is chromic oxide. So we prepare nitrogen from ammonium dichromate. You can get this ammonium dichromate by mixing potassium dichromate with ammonium chloride and heating that mixture. When you take equimolar of potassium dichromate and ammonium chloride, you can get ammonium dichromate. And the next preparation of nitrogen is by thermal decomposition of sodium or barium azide. You can prepare very pure nitrogen by this method. Sodium azide is NaN3, barium azide is BaN3 twice. Why we are putting twice here? Because barium is Ba2 plus, stable oxidation state, whereas Na is Na plus. So when you heat sodium azide NaN3, you get 2 Na plus 3 N2 dinitrogen gas. Same way, when you heat barium azide, you are getting barium plus 3 N2. So you can prepare very pure nitrogen from sodium and barium azide. And this thermal decomposition of sodium azide is used to inflate the airbags used for safety devices in some cars. When the car meets with an accident, you can see an airbag getting inflated, and that inflation is done by this reaction, thermal decomposition of NaN3. Actually, when the accident occurs, the sensor provided in the car detects the collision. It sends an electrical signal, and that signal overheats and ignites sodium azide placed in the airbag. So inside the airbag, you will be having the sodium azide. So that will be ignited when the collision occurs, and the electrical signal is sent to that. And this sodium azide in the airbag is a fast burning fuel that produces large amounts of nitrogen gas. And that nitrogen gas goes through filters and then fills the nylon airbag. And the airbag then just hits your head and protects you from injury. So this reaction actually takes place inside that airbag. After your head hits the nitrogen filled bag, it deflates, which means all the nitrogen gas comes out through the tiny holes. And the nitrogen gas that is released is absolutely harmless because nitrogen constitutes about 78% of the air that we inhale. So that nitrogen which is coming out of the airbag is harmless. And you would have seen a cloud of smoke that fills the vehicle, that is actually talcum powder or cornstarch, and that prevents the airbag from sticking to itself when it is folded inside the car. So before it is inflated, when the collision occurs, the airbag will be folded and it will be inside the car. So to avoid sticking to itself, it is filled with this talcum powder or cornstarch. So this reaction is actually taking place in that inflation of airbags that is used for safety devices in cars. So we have prepared nitrogen. We have seen two different preparations, commercial and laboratory preparation. Under laboratory preparation, we prepared nitrogen from three different reactions. First one with ammonium chloride and sodium nitrite, and from thermal decomposition of ammonium dichromate and thermal decomposition of sodium or barium azide. Now we will see the properties of dinitrogen N2. So we're going to see the physical properties and chemical properties. First, when you look at the physical properties, dinitrogen is a colorless, odorless, tasteless, non-toxic gas. And nitrogen has two stable isotopes, N14 and N15. You know what are isotopes? Atoms of the same element having different mass number. So nitrogen has two stable isotopes, N14 and N15. And nitrogen is very slightly soluble in water. So when you take 1 liter of water at 273 Kelvin and 1 bar pressure, you can dissolve 23.2 centimeter cube of nitrogen in 1 liter of water. And the freezing and the boiling points are low. Freezing point is 63.2 Kelvin and boiling point is 77.2 Kelvin. So these are the physical properties of dinitrogen. Now coming to chemical properties, dinitrogen is very little reactive chemically under normal conditions, and it is neither combustible nor does support combustion. And you know, dinitrogen, two atoms of nitrogen are joined by triple bond. And due to the very small size of nitrogen atom, the triple bond length is also quite small. And as a result, the bond dissociation enthalpy is quite high. So it is difficult to break this bond. But you can make dinitrogen combine with metals, non-metals, as well as certain compounds under strong conditions. But at room temperature and in normal conditions, this dinitrogen is inert and unreactive. It is because of the high bond dissociation enthalpy. But it becomes reactive when there is increase in temperature. So reactivity of dinitrogen increases with increase in temperature. So under that conditions, dinitrogen reacts with active metals. Look at this example. Li is a metal. Nitrogen reacts with Li. 6 Li plus N2 gives 2 Li3N. See, balancing this equation is very, very important. So always write the balanced equation. This is a lithium nitride. Same way, nitrogen reacts with magnesium. 3 Mg plus N2 gives Mg3N2, which is magnesium nitride. Same way with calcium, it gives you calcium nitride. See, this happens when it is heated. So heating symbol should be written here. So when it is heated, nitrogen reacts with active metals. Same way, nitrogen reacts with dihydrogen. And this reaction where nitrogen reacts with dihydrogen is called as Haber's process. It's one of the industrial process for the preparation of ammonia, and it is a reversible process. Nitrogen reacts with 3 hydrogen to give you 2NH3 at 773 Kelvin, and this takes place in the presence of iron, Fe. You'll be learning in detail about this reaction and the experimental condition when we learn about ammonia. So this reaction is an exothermic reaction and the heat released is minus 46.1 kilojoule mole inverse. And now reaction of nitrogen with oxygen. Nitrogen reacts with oxygen at about 2000 Kelvin temperature to give you 2NO, which is nitric oxide. So we have seen the chemical properties of nitrogen, where it reacts with active metals, with dihydrogen and with dioxygen. So all this takes place not at room temperature, because nitrogen is inert and unreactive at room temperature because of its high bond dissociation enthalpy. And now coming to the uses, here I told you this reaction is used for the manufacture of ammonia. So nitrogen is used for the manufacture of ammonia. It provides an inert atmosphere in some reactions or processes where you want some gas which should not react with any other reacting species there, and you want to provide an inert atmosphere, then we prefer N2 gas. And N2 is used as an inert diluent. Again, inert means it will not react with any other species, but it will be helpful in diluting that particular substance. For that purpose, we use nitrogen. And nitrogen is used as a refrigerant. As it provides that cooling effect, we use nitrogen as a refrigerant. Same way in cryosurgery, the surgery which is taking place at a very, very low temperature. When we say cryosurgery, it is actually the use of extreme cold in surgery to destroy abnormal or diseased tissue like tumors. So for that purpose, we use dinitrogen. So under the compounds of nitrogen, we have seen dinitrogen, and we have seen the anomalous nature of nitrogen also. Thank you.